Hey there, Internet. Today I'm going to talk about my multimeter and why. What this video is about is a dedicated continuity tester. I have wires everywhere, and sometimes they get a little bit out of control. The multimeter cables that you typically get for probes are about 6 feet long, and they're always falling off the desk, pulling on whatever I'm working on. They're getting in the way of opening a drawer. They're just generally kind of a nuisance. And if I want to do some simple continuity testing, I just continue to find myself annoyed at the wires and how long they are, and having to mess with the timeout on the continuity tester, and it's always beeping at you, trying to get you to do something because it's timing out. So I looked around. I found a couple solutions for different ways that you can make dedicated continuity tester. The other thing, though, is I bought these probes, and this is a really, actually very good probe kit. I bought a few probe kits just to test different ones out. This one here is really pretty great because you just get all these accessories, and the accessories are really high quality. I really like these alligator clips. Everything in here is pretty well made. But I had extra gold tips, and so I've got some other probes. They're the standard nickel plated or whatever they are, and they're just not as good as the gold tips. The gold tips, give you if you're doing continuity testing, they give you a good signal immediately. I have some tips in these probe holders, but I wanted to use the tips that I didn't actually have installed. So I decided to make some new probe holders, and then also to make a dedicated continuity tester. Leo's bags of tricks I found while perusing through different folks' implementations, and he's got a pretty nice solution here. This thing can be plugged into 220, 230 volts and survive without any issues. The video, the Ultimate Continuity Tester, I'll leave a link below. This video walks through this entire circuit and why all these components are in here and what all the different components do. This is a really good detailed explanation of kind of the Ultimate Continuity Tester. I don't have some of these components, and especially this big shunt switch. I don't even know what you call it. But go ahead and watch this video if you're interested and you want to build something even better than what I'm going to walk through today. But I think this is good. I just don't have the components. I also found this tester here, and I thought this was very good. Unfortunately, the code, it's not in Arduino, and it uses all the low-level AVR bit shifting stuff that my brain just cannot seem to retain. I didn't want to spend hours and hours and hours in the data sheet and trying to re-understand how all the bit shifting works. So I found what is going to be ultimately the solution that I am going to talk about in this video. And this is it. It's got a simple diagram. The code's pretty straightforward. This is the PCB that this guy made, and it just seemed a simple solution. I'm going to be probing mostly milled PCBs that are not active circuits, and so this seemed like a pretty good compromise. And he's got a couple requirements in here. It's small. This ATtiny85 is extremely small. Mine ended up being about it's about 2.5 inches by a little less than 2 inches. So it's pretty small footprint. He wanted to have a 50 ohm threshold, and I actually wanted to have a little more configurability here, and I'll talk about that later. It's very fast, so this is absolutely true. It picks up the signal right away. The current is extremely low, and this is maybe the best thing. There's no on-off switch. It essentially monitors the circuit itself, and if there's no activity after 60 seconds, it'll go to sleep. If it detects if the two probes touch each other or there's continuity, it'll actually wake up out of the sleep. And this should run on a coin cell battery for quite a long time. So this is what I ended up choosing to implement. I didn't do it exactly like this guy laid out, but I'll go ahead and walk you through the circuit diagram, and then I'll show you the PCB that I laid out and created and soldered up. Here is the circuit that I ended up using. There's one or two small changes in here. The first change is adding a resistor. It turns out, for whatever reason, my result turned out a lot better when I added a 220 ohm resistor in series with the piezo speaker, and that's what this part is here. I added a second LED because I had a second design that I worked on. I didn't end up using that in the code that it was flashed on the ATtiny85 that I actually used. So this, I think it's this LED here, does not really need to be implemented. So you could skip these parts. The way that this works is the pin 5 is used in the analog comparator on the AT85, and essentially what the comparator is going to do, it's going to compare two voltages. And so I've got pin 5 going up here to 3 different switches, and those switches allow me to turn on a reference connection to 3 different resistor values. So I've used a 10 ohm resistor, a 50 ohm resistor, and a 10K resistor. And so those just connect pin 5 down to ground through the switch. Pin 6 is my probe pin. This is actually named wrong. So this is my probe pin, this is the ground pin. When these two are connected, the comparator will look at the voltage across these 2 pins and compare it to the value that you get with whatever resistor you have turned on here. There's a power LED that gets current limited with a 2.2K resistor. Again, there's another LED on this side that you could blink, or you could change the blink frequency based on the measurement. You could use the ADC to try to measure the voltage and get a value or resistance value. Again, it's not being used in this particular circuit. We've got a decoupling capacitor here connected up to VCC and ground, and then we have a 1 pin for ground for the battery connector, and then we have 2 single pins for a piece of wire that's going to strap across the top or the positive terminal of the battery and then hold it down against the negative ground pad, and that'll supply power into the system. The final thing is just a simple switch connected between pin 1 and ground, and this is the reset switch. So this allows me to reset the ATtiny85 in case it starts misbehaving for whatever reason. And I think I've covered all the components. So those components are pretty straightforward. Again, if you look at the original design here, there's no there's no resistor in between the piezo and the ground plane, and I think for whatever reason the piezo speaker that I was using was just causing problems because there was no current limit on this pin. So the code for this is on GitHub, Technobloggy continuity tester. I'll leave a link for that as well down below. It's really straightforward. I mean, there's only 70 lines of code. Again, it's got all this low level bit shifting and stuff happening, which always my brain can't quite retain exactly how this works. So essentially what this does is there's an interrupt routine here that's going to update a timeout value. So whenever the interrupt gets thrown, the time value will get extended. So there's a 60-second timeout that this will go ahead and update. This might wrap, and I have some weird, it does seem to blip around a little bit. You can see the LED will pop off from time to time. I'm not sure if that's because this value gets wrapped or not. It's probably moot. It doesn't really seem to affect the operation of it. This interrupt will update the timeout if it's being used. There's also a check of the comparator that happens right here. And if we get the result for continuity that we're looking for against the reference network, it will go ahead and call this beep routine, which will tell the piezo speaker to generate a tone. If the timeout has expired, it'll go ahead and turn the LED off and shut the system down. And then that'll wait for a pin change interrupt between the probes, and that'll go ahead and wake the whole thing up. So this is, again, really straightforward. Back to the EasyEDA. Here's the board design that I came up with. This isn't really optimized for space. This is a single-sided board. Up here we've got our 3 switches for our reference network. So this will be the 1K, the 10 ohm, this will be the 47 ohm, and this will be the 10K ohm. And those all get connected down here to pin 5. The probe jacks typically are 4 millimeters. So I just soldered in a couple 4 millimeter shunts. These are 6 millimeters across, and the actual pad is 10 millimeters across. So if you can imagine, the shunt's going to fit in there with a little room around to solder to. The battery connector, here's the 2 positive terminals are J4 and J5, and this is the negative terminal. What I did here is I just made the pad 20 millimeters across, and so that worked out pretty well. Here's the switch for the reset. I've got the 2 LEDs and their associate resistors here and here, and then up here I have the little resistor for the piezo down to ground. So this is a really straightforward prototype board, and it was pretty easy to put together for EasyEDA. The traces I picked are 1 millimeter, and there's a 0.5 millimeter isolation route around all the components. And this came off without any issues at all. I literally videotaped the whole process of creating this, and it's pretty boring. But if you're interested in watching me actually go through the thought process of creating the board, creating the PCB, and using all the functionality of EasyEDA, just go ahead and leave me a comment down below, and I can look into making a more detailed video about the actual design process.
And I'll grab the drill file and the top layer file. Those are the only 2 I need. So just these 2. I just drag them in here. That's our board. Looks good. So my tool needs to be 0.45. I'm going to do 2 passes to clean up the burrs. 80% overlap. And generate full geo. That looks good. So the overlap here is, these are the 2 passes that it's going to make. So it's just going to overlap those just a tiny bit, 20%. The overlap. It's 80% in the settings, but there's only 20% overlap in the thing. So with a 0.45 millimeter tool, we'll end up with a 0.5 millimeter isolation. And just eyeball it and make sure that the cutter is going everywhere that you want. This looks good. So go ahead and click generate, save G code. Put it here, call it traces. So that's the traces are done. The blue line is going to be the part that gets cut out. Now, go back in here. I want to do the board cutout, and this basically takes the Gerber file and tries to figure out the outer boundaries of the Gerber file. And so I just click rectangular, and that's going to create this geometry. Then I go into here before I do anything else. I want to do a mill geo. you can do drills, but then you have to do tool changes for all your drills. If you mill them, it'll interpolate the holes. So I have a 0.8 millimeter end mill, and it'll interpolate those holes with that. And I don't want to do anything with that file. I want to combine it with the cutout file that I just made. So join Gerber, Geo, whatever, join everything command. Then you go in here, my board is 1.6, so I'm going to make that minus 1.6. Multi-depth, 0.4 per pass. And that is it. Enter it. So you can see it's going to interpolate this, drill all these different size holes, make our holes for our speaker, and then we just call this drill and cut out. That's it, we're done.
Okay, so here is the board. Just test fit this in there. I'm going to lose this little tab, but that'll solder right in. Button fits. So what I like to do is jot down the different components. All right, so here it is. We'll give it a test. I really don't like the battery holder. I have to get a better solution for that. The other thing I'll just point out here is the LED that I put over here. I actually didn't, I put a different version of the code on that's not actually using that pin. So I was actually troubleshooting that a little bit, but everything seems to be on there right, and then I remembered that I used a different version of the code. So anyway, so if you can hear that, there's a residual tone, and it's just very intermittent. I don't understand what it is, but it just kind of pops in there. But if I get continuity, I can definitely hear it. So it's quick. There's that tone again. So that board seems like it's good. Here's another board. These are ground anyway, so that's pretty nice that it's that responsive. I can just drag it because my meter is not that responsive. All right, so the other functionality here is this network of reference resistors that I put in here. So if the switch is up, it's off, down is on. So if I turn on the 10K reference resistor, this is 52K, we get nothing. This is 219.4K, no problem. And obviously anything less than that, it will detect. So then we can turn that off. Well, the next one's actually 47K, so this one's right on the bubble. You can hear it. There's some oscillation likely in the comparator, and so the tone's a little wonky. That one will work fine, but if we do the 220, it will not detect it. So no continuity. And then if we want to set it to 10 ohms, 220, nothing. 47. We get a real rough sound. I wouldn't call it a tone at all. And then for the 10 ohms, 10.3 ohms. So if this is a 10 ohm resistor and I have, a few ohms in the probe and the wires, that works. So yeah, that little change works. Now, if I'm doing a PCB and I want to test to see if there's any little fur down in there, the 10K setting might be the best setting for me. If I'm testing a circuit and I really want to make sure I got the continuity that I'm looking for, I might want to switch on the 10 ohms and make sure we've got a real good connection. So anyway, that's the reference network. Now this is a piece of 5mm steel. I didn't have a shoulder to just put a single nut on, so I just used 2 nuts and this crimped on fitting, and I just cut a 5mm thread on that. And then on this side, the heat shrink was a little bit long. I have to trim it off, but these are from a set, and they came with a whole bunch of tips. And I really like these probes. They pop out. There's a bunch of different adapters. These real nice alligator clips. It came with a whole bunch of stuff, but I wanted to use some gold-plated tips because they're just so much more responsive than the really cheap probes. So that's the whole reason I made this thing. So I just tapped this for 3mm. And then screwed the extra tip that I had, one into each one. So there's 2 3mm taps going in there. So I played around with a couple different versions of this code. In the ones that I tried out, I could not get the beeper to work after it woke up. The beeper just got into this wonky state, and you'd have to reset it. This one works, and I can live with this weird tone. What I don't understand is why it seems like it resets itself every now and again. I don't know if it's getting. You see right there? It just blipped out. That should not be happening. There's no rhyme or reason to it. There, I did it again. So yeah, I don't know. But this will go to sleep after 60 seconds, and then it'll essentially turn on a pin change interrupt. And then anytime that these go low again, the board will go ahead and wake up out of sleep and start processing. So it really, I think it draws, when it's on, it draws 2 milliamps. And it could go as low as 1 microamp when it's in its full sleep state. It turns the pull-ups off and everything. So I'll post a link to the code. And again, if you have any suggestions on how to fix the weird kind of residual buzz, or how to fix the kind of the wonky behavior where it seems to be resetting, let me know in the comments. Anyway, hope you enjoyed this. Hope you can make one of these or make a better one of these. And thanks for watching.